Chapter 14, Kinetics, Exercise 14.109. Anthropologists can estimate the age of a bone or other samples of organic matter by its carbon-14 content. The carbon-14 in a living organism is constant until the organism dies, after which carbon-14 decays with first-order kinetics and a half-life of 5,730 years. Suppose a bone from an ancient human contains 18.5% of the carbon-14 found in living organisms. How old is the bone? First, we look at this percentage. 18.5%, lower than 25, larger than 12.5%. That means this percentage is below a quarter, greater than 1/8. Therefore, the age of the bone should be between 2 times the half-life and 3 times the half-life. Alright, I'm going to just estimate it should be around 15,000 years. Now let's do the calculation. There are different ways of doing this calculation, but I'm going to show you the more systematic method. Given the half-life, we can compute K, the rate constant. K is simply Ln2 divided by half-life. Now we have K. This is the first equation we use. We get the value of K, and here K is in the unit of year to the power of -1. Alright, and then 18.5%. Alright, this is going to be the concentration of carbon-14 in this bone divided by the initial concentration of carbon-14, just when the human died. All right, so it's a ratio here, 0.185. all right, is equal to e to the power of -kt, and we're solved for t. The value of k is given, it's just this, and then we can use this equation to solve for t. But there's a trick. Why don't we take the logarithm of both sides? Alright, so we have -kt on the left hand side, and we take logarithm here. Alright, so, and then what we do is this k is this. Alright, k is this. And then we solve for t. So now it's pretty simple. T is simply the logarithm of 0.185 divided by Ln2, and then times 5730. That's it. Alright, so what I will do is I will do the multiplication first. Alright, by multiplying both sides by 5730. So we have something like this, and we put the negative sign here. Alright, and then divided by Ln2. Both sides divided by Ln2, we get t. It's about 14,000 years. Alright, so I estimated between 14 and 15. So I have overestimated this number. Alright, submit. That's the age of the bone. Now I'm going to show you a trick, which is super easy. If you have the percentage x, alright, just take the logarithm of that and divide it by Ln2. Alright, and then times the half-life. That's it. You're going to get a negative number, but don't worry, just change it to positive. Alright, so that's it. So whatever questions about first order kinetics, you can do this if you are given half-life. Alright, if you're given half-life. So maybe I should just show you the more general equation here, and of course in the end you need to use a negative sign here, and then that's it. This is how you estimate the time period given the half-life and the percentage of the concentration compared to the initial concentration. Alright, So this X really is the ratio, all right, between the concentration at time t and the initial concentration. All right. In this case, we have 18.5%. All right. So you just plug it in, 18.5%, and we have the half-life. That's it. I got 14,000 years again. So I often use this trick to quickly get the value of the time period, given the ratio between the concentration at time t and the initial concentration, and given the half-life. You can just do this.